No. All right, so we're looking at 68 for those of you who are playing along at home. We got a northward vector, 500 kilometers an hour. We got one coming from the northwest. Now, of course, northwest is there, but it's coming from the northwest. So I'm actually going to draw it like this. And that's 50 kilometers an hour. So I probably should have made that shorter, but too bad. Redo that so this makes a little more sense visually. All right, that's 500. So here's 50. Beep. So I want to add these vectors to see what the actual, you can do it, Jeff, direction of motion of this plane is. So this would be easier to add these vectors together if I knew the components. I really want this to make sense. So if I blow up this one, this 50, let me blow this up so I can look at it. Can you figure out the components of that vector? Right? We know what this angle is. Are you guys with me out there? Is it hard to add? Can you add these vectors here together for me? 207 and plus 0, 3. Can you add those vectors together? Up here?
Yeah.
Yeah, that's easy as shit, right? Correct? Is it okay for me to say that? Do I make anybody feel bad?
With me at least.
210. Oh my God, that was hard, right? So if I have them broken into components, I can add them together. Now you got to be careful. You do have to be careful. This is obviously going to be negative, correct? And this will be positive.
Yeah.
If you can write these vectors in components, you can then add them together. So for example, this one, I'll go ahead and do it's 0, 500. Well, that was hard. Now, if you guys can break this guy up into components, you can find the final vector. Then you can find the angle. How would I find the angle this vector makes? Isn't this x and this is y? How would I find the angle that that vector makes?
Inverse tangent.
Yeah, inverse tangent of y over x. Throw that in the old calculator. So down here, once I combine these, now doesn't this make sense? Please let this make sense. If I've got my plane going 5 miles an hour, 500 miles an hour, and I got a wind coming at me, am I not going to be going slower? If that wind is pushing, is not just coming straight at me, it's coming at me at an angle, is that not going to make my plane go a little bit away from it? Isn't it going to push it? Yes?
Yeah, that makes
And
sense.
if I don't correct for it, which is part of what this problem is suggesting, then I'm going to be off course. So that's what they want to know, is how far off course would you be? So all you have to do is get them written into components, add them together, and then figure out the angle that it creates. And it'll tell you how far off course you will end up going. Does that help? No? Who asked the question again? I'm sorry. Oh, wait, there's a chat. I can't handle all this. Okay, that does help. So let me look at number 42. I'm going to erase all this. You guys ready? All right, it's going. Oh, could you please do something like 64? Okay, I will next. The next question is 42. All right, let me clear this away. Clear. Oh, okay. So, all right. All right. This is kind of nice that they gave us all this grid kind of stuff to do. So if I wanted to add a vector to another vector, I don't know why I made them like this. I want to do it visually. Please tell me you remember doing this. I make a little parallelogram. I draw something parallel to V and something parallel to U. And then I connect these together, and that's the answer. Oh, crap. And hopefully you do it straight. Okay. So this would be U plus V. So do something similar here. Right? And the first thing you got to be careful about is it says 2U. How do you make 2U? This is U. How would I make 2U? Isn't this up 1 over 3? When I just go up 1 over 3 again, and wouldn't that be 2U then? Are you guys okay out there? Do you guys understand that?
It just seems likely. Yeah.
Seems likely.
Yeah.
No, it's more than likely. That's exactly what you do. So 2U just means take U, and then on top of that, give me another U. So this would be 2U, and then you do exactly like we did here. Right? You draw V, and you draw this. Can you see how? All right. So this would be 2U. That's not horrible for me. That's pretty good. So that's another U, right? So this overall, this is 2U. All right. Excuse my going off course there. Let me see. What's going to put in? Oh, okay, okay. I like that sound. And now you do exactly what I did here, but you just, the beautiful thing is, do you see how you've got some help? See how this is one more U there? And then I guess you got to do another U. And then you can connect this. Doesn't V go down 2 over 2? So can't you go down 2 over 2 to make sure that you end up in the right place? So the fact that it's on a grid makes it a little easier than just sort of like estimating it just out in the air. Sounds like that's better. You're welcome. So they gave you the grid stuff here to help you precisely plot the vectors as you need them. Right? This is fine for an estimate, but I'll bet you that's not really parallel to that. I did a horrible job. You guys see how that's not really parallel to that? So it's easier if I have grid to kind of keep me straight. I am grid. Okay. Yes, that happened. Anything else, guys? Any more opportunities for me to make a strange Guardians of the Galaxy reference? I'm sorry, 64. I forgot you asked about 64, and you asked so nicely too, twice. God, what kind of a jackass am I? All right, 64. Now this sounds like a joke or something. A woman starts walking from home and walks 4 miles east into a bar. The barman says, no. Yeah, this is a neat one. Do you see all the vectors involved? She walks 4 miles east, and then on top of that, 7 miles southeast, and then on top of that, 6 miles south, and then on top of that, 5 miles southwest, and then on top of that, 3 miles east. How far has she walked? So, all right, now watch, guys. I want you to understand how beautiful this is. Let's focus on 2 of these. Are there any 2 vectors going in the same direction? Yes. Do you guys see 4 miles east and 3 miles east in the same direction? So couldn't I just kind of erase this and erase this? And then I've got one vector that represents both of those, 7 miles east. Do you guys understand so far? Isn't that make this, if at some point you go 4 miles east and then at some other point you go 3 miles, you went frickin' 7 miles east, right? Okay, now there is more eastward motion, isn't there? Thanks for that, Kurt. There's more eastward motion in here, isn't there?
5 miles southeast, or 7 miles, sorry.
That's all right. So this is 7 miles southeast, which would be, Jeff, why are you forgetting what east is? There we go, Jeff. So this is 7 miles southeast. how much of that motion is pure east? So this is I always do this. I always draw these pictures so small, but I don't have a lot of room. So here's 7 miles southeast, 7, right? So how much of this is pure east?
7 rad 2 over 2.
Yeah, now go a little bit slower. We obviously know this angle is 45 degrees. So this would be 7 times cosine of 45, which is rad 2 over 2. Are you guys understanding? So watch this. This is so cool. This is so cool. And then somebody else tell me, what is this?
Exactly the same.
Yeah, except
It's negative.
negative. I like it. So this would be -7 rad 2 over 2. And this is in what direction? Oh, let me just make it plus, but as long as I say it's in what direction? What direction is that going in? This is east.
South
This
or
is
east.
south.
Yeah.
So can't I put that together with this?
Yeah.
So don't I have 6 plus 7 rad 2 over 2 south? So what I'm saying is, you can break like this 5 miles southwest, right? You can break it up into a south piece and a west piece. What do you think I would do with the west piece? Is everybody, let me make sure everybody, so this 5 miles southwest, can't I break it up into a south piece and a west piece? Yes?
Would you also add the 7 rad 2 over 2 to the
That's what
7
breaking it up
miles
into those
east
pieces
first?
means. It would have to be 5 cosine of 45 degrees and 5 sine of 45 degrees, exactly like we did over here.
I'm
Yes.
saying you added the 7 rad 2 to the 6 miles south, but wouldn't you add it also to the 7 miles east that you first made?
Yes, this piece, yes. So this would be +7
Yeah.
rad 2 over 2, exactly. Now, coming back to this guy. What was I saying? I forgot. Let me think. Yeah, you can break this up into south and west. And what do you think I'm going to do with the west piece? I really want this. Are you guys good? Sorry?
So let's start from the east.
Yes, I'm going to subtract it from the east because west and east are of opposition, right? Isn't west sort of like the negative direction on my little axis here? So what I am saying is if it's not a pure cardinal direction, break it up. Let me see, what am I getting here? All right. So let me ask you, oh, okay, shit. If I went, all right, let me erase some of this stuff. I don't know if you guys are copying this stuff. I'm gonna erase all this. You ready? Okay, do what you gotta do. This is all going away. Gone. All right, so what I'm saying is this is really easy, right? 4 miles east and 3 miles east. That's easy. That's freaking 7 miles east. So if I take something like this and I break it up into 5 rad 2 over 2 south and where'd it go? 5 rad 2 over 2 west. Then I can put that piece together with this piece. Yes? Yes?
I'm just kind of wondering, do you have to set a component for every move, or you can just
For every, sorry, say it again. You have to set component for
every move,
every move. I don't know what you mean.
like 4 miles east, 7 miles southwest. So that's east.
See, this is already broken into components
Oh, okay.
because it's pure east. This one I have to break into components because it's a mixture of south and east.
Yeah, I'm saying, do you have to use the like bracket?
Bracket. No, you don't.
No.
I didn't. I could say that this becomes, it really depends on what you want to call positive and negative here, but it becomes So if I call south negative, this would become 7 rad 2 over 2, negative 7 rad 2 over 2. This I could look at as, you could do it, Jeff, 4, 0. Does that make sense to anybody? So if this is my east, Jeff, red's not going to show up well on red. Oh boy. If this is this, then 4 east is written as 4, 0. Yes, 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 yes. And then 7 miles southeast is written as a part east and a part south. So yeah, you could write it like that if you want to, but you don't have to, because I didn't in the first place, right? I just wrote them as so much south and so much west. So you can represent them in vectors if you want to, but you don't have to. How do you guys feel about what's happening right now? What's going on? So if I break down the vectors that are like combined cardinal directions, break them up into their parts, right? Couldn't I put the 4 miles east together with the 6 miles south and make so much southeast? Do you guys understand what I just said? If I go 4 miles east and 6 miles south, didn't I go some amount southeast? It would actually be like a little off from southeast, but do you understand my basic point? If I went 4 miles east and 4 miles south, didn't I go some amount southeast? What's happening out there? Didn't I? Of course I did. If I go south and then I go east, I could accomplish the same thing by going some amount southeast. So all I'm saying is do that in reverse. Take this, it's south and east put together, and break it up into its parts. Break it up into its southerly part and its easterly part. No, you guys, I can't. I need a reaction. I need some indication of if this is making any sense.
I think it makes sense.
Think so. All right. So one thing you could do, sorry.
What do you do once you have the south and the east, though?
So one thing you can do, you got your east, you collect all that together. You got your south. And to be honest, this is west and east, and this is north and south. I really want this to make sense. Like, okay, look, what do I have under east? I've got 4 miles east. I've got 3 miles east. And then I've got 7 rad 2 miles, 7 rad 2 over 2 miles east. And then I've got 5 rad 2 over 2 negative because it's going west. Do you guys understand what I just wrote down? I wrote it very small for some reason. I'm sorry. But then I just add all those together. And that's my total easterly direction, correct? Now I do the same thing with north-south, although I don't think anybody's going north at all. Nope, she didn't go north at all. So now I just get all my south. I get this piece of south. I get this piece of south, and then I can combine all those together. Now, once I get all that, let's say I get 8 south and I get 3 east. Can you figure out what the direct line would be to get to her house? Because here's her house, right? She goes 8 south and 3 east. That must be where her house is. Well, what if she would have been able to walk straight to her house? Can you figure out how long that would have been? Isn't that just Pythagorean theorem? Pythagorean. Now, the first question here is kind of silly. Do you guys understand that first question is really, really silly? You just have to add 4 miles and 7 miles and 6 miles and 5 miles and 3 miles. Okay, that's how far she walked. And then they're saying if she would have went straight home, how far would she have walked? And that's just finding this. That's just finding this hypotenuse. Does that make sense, guys? So instead of going, you know, what if she would have just freaking walked straight? That's what that's really asking. Okay. All right. That's all I'm going to say about that. That's all I got to say about that. All right, let me clear that away. Anything else, guys? Did I miss anything? No. Okay. All right. Anybody else? Anything else from homework, guys? All right. So we're going to get back into, oh, by the way, what is happening today?
Quiz.
Yeah, buddy. Quizzes. We love them. I keep giving plenty of them to you.
They're better with pie.
This is true. Almost everything's better with pie. Anyway, all right. And then Cool Whip even makes that better. So I think if you can remind me, I'm pretty sure I sort of said a little bit about matrices. I'm pretty sure I did. I said like the tiniest bit. And I don't know, you guys got to get into the partial fraction section and try some of this out. So you have some questions. So what I want to talk about is matrices, obviously. I want to explain how matrix multiplication works, and then we'll do like maybe a little tiny bit out of the next section, and then we'll call it a night. See what happens. Oh, let me turn Bernie off. Sorry, Bernie. It's okay. I understand. All right. Thanks, Bernie. You should apologize for the horrible rendition of Bernie. I used to do better Bernie. I don't know. Let me just stop doing that. All right. Thank God. Wow. I don't know what the hell is. Okay. Whew. Oh crap. All right. So let me, all right. A matrix. Now, the funny thing about matrices, they have many different interpretations based on what you're using them for. Let me try to jerry-rig this thing so it doesn't drive me crazy. It's too much, Jeff. Let's see. Is that good? We'll find out. All right. So you could look at a matrix as, so here's a 2x2 matrix. This is a 2x2, 2 rows by 2 columns. Right, 2 rows by 2 columns. Okay. And you can look at it, again, there's a lot of different ways to look at a matrix. I can't explain all of them to you because some of it relies on math you don't know yet. What are you doing? Okay. This can be looked at as 2 ways. I can look at this in a couple different ways. I can look at this as the vectors A, B, and C, D. Or I can look at it as the vectors A, C, and B, D. Okay, and I think I said this last time. I can look at it as a collection of row vectors, or I can look at it as a collection of column vectors. It depends on the application. It depends on what I'm trying to represent with the matrix. It depends on what I'm trying to do with it. And sometimes it doesn't depend. I can look at it either way. So it's kind of a way to stack vectors all together. Now, let me just say one thing that we're not going to get too deep into here. This is like further in mathematics. A matrix is a transformation. I can apply it to something and it would transform it. So for example, cryptography, encryption. If you want to encrypt something, you can actually use matrix to do it. If you want to play with an image, change the brightness or something, I can actually act on the pixels with a matrix. And it would transform the picture. All right, this is a little too much to get into. So that's another thing about matrices that you learn much later. They can be looked at as linear transformations on something. That's a little too much right now. We don't need to look at it like that right now. Right now, we're looking at it as a collection of vectors. All right, this is going to become huge later today. Okay, so how do I add matrices? Well, if they're a collection of vectors, I add them the way that I would think I would add them. So if I added the matrix 1, 2, -1, 3, and I wanted to add to it the matrix -4, -2, 6, 1, you would hope it would just be adding each piece, and thankfully it is. And why does it make sense that it is? Because I can look at it as a collection of vectors. And how do I add vectors? Component to component. Everybody with me so far? So what is this, of course?
-3,
-3,
0,
0,
5,
5,
4.
4. Okay. Become a -3. All right. Man, let me do this. I always hate when. Hold on. There. All right, let's see if that. All right. That'd be fine. Okay. Now, so that's that. Thank God. That's some easy shit. This is a 2x2. This is a 2x2, and that's why this is possible. You can only add and subtract matrices that have the exact same dimensions. Because, Jeff, there you go, buddy. All right. If I try to add this matrix to this matrix, I can go, okay, 1 + 1, 2 + 4, void, +7. It's not even 0. It's not even 0 here. It's just absence of anything. I cannot add these together. This is how big is this matrix? What's the dimensions of this matrix?
2x3.
No.
3x2.
3x2. So it's always rows by columns. Rows by columns. 3 rows, 2 columns. This one is going to be
2x3.
2x3. I like it. So obviously not the same dimensions. I can't add or subtract those. Okay. That's nice, right? Let that be nice. So adding, subtracting matrices, easy as shit. Yay. All right, so if I let A be the matrix, B is this matrix, and C is all right. Now, obviously, if I ask you what is A plus B or C, can I do this? Can I do A plus anything up here?
Nope.
No, I can only do A plus A, which is kind of silly. What's 2A? So let me see. What is 2A? What's your gut tell you? What's 2A?
Multiply by 2.
Yeah, so then you're gonna get 4, 8, -2, 6, right? You guys with me? because 2A is A plus A. What is B minus 2C? Take a minute and figure it out. What is B minus 2C? Don't say anything. Just figure it out. Here, I can just teach like this. Do B minus 2C. So what I would do is this. I would multiply C by -2. You don't have to do like me. I could be just a crazy person. So now it's easier for me just to see what this is. 2, -9, 1, 0, 0, neato, 11. Okay. Is that all right? You guys okay? Made me laugh too hard. I don't know what just happened. Okay. All right. So
It was the puppet hand. I'm just lagging.
Oh, the puppet hand. Okay. Okay. Let matrix addition and subtraction and scalar multiplication. Let it be easy. It is easy. Thank God. Why is it so easy? Because we built it off of vectors, and vectors are actually relatively easy to add, especially if they're broken down into components. So this is the components of the vectors. So if I can see those, easy. What is not easy necessarily is multiplication. Now, to be completely honest, I'm about to show you an idea about why matrix multiplication works the way it does that I never thought of until about 22 minutes ago. So I'm excited. And it's kind of cohesive. It's hard to fully explain without going deeper into matrix stuff. But let me see if I can make this make some sense. So remind me, how does a dot product work? Like, what is the dot product? What is this dot product here? How do you do a dot product? Does anyone remember?
Yeah, you use I and J.
If you want to, you don't have to.
Like 4
Yeah, 1 times 4
plus 5.
plus -1 times -5. Just to show it all the way out, right? Because the cross, so I dot I is 1, J dot J is 1, J dot I is 0, I dot J is 0. We talked about all that behind the scenes. So now I can just use the shortcut. It's component times similar component plus the other component times similar component. Bam. So it's 4 plus 5, 9. Like it. Okay. Now, remember how I said, oh, let me see. Here's what this would look like in matrix form. So we had some decisions to make, and here is the decision that was made. It didn't have to be the way I'm about to show you. So if you ask me, well, why didn't they just do it this way? It will actually make more sense once you get a little deeper into matrix stuff, if you ever do. But it was just a choice that we had to make. So what we decided to do is, let me see if I can write this the right way now. Wait a minute. Yes, okay, all right. If I write, that is a matrix, but it is also this vector. All right, this gets a little bit weird. But a matrix is just a stack of vectors. And if I just have a stack that's 1 vector tall, it's just a vector. I don't know if you guys are with me. I've written it as a matrix, but it actually represents that vector because there's only one vector in it. So matrix is like a collection of vectors. Okay. Now, I'm going to write next to this a vector written vertically. So the way we chose to do matrix multiplication is that any matrix that's written here, I consider the vectors this way. Any matrix written here, I consider the vectors this way. So if I want to represent this dot product, I have to put this one this way and this one that way. Just please stay with me. So this is what this looks like in matrix notation. And remember, a matrix could have vectors like row vectors, or it could have column vectors. So we decided what's written here, we assume it's row vectors. What's written next, we assume it's column vectors. And then I just do a dot product. Wouldn't this be 4 plus 5? So I would go this way, that way. So I go this times this, plus this times this. Okay, again, I completely understand if in your head you're going, why did they choose that? Well, because they had to make a choice. There had to be a choice as to what recipe kind of thing to set up. And this choice makes sense with a lot of the things that we want to do with matrices. And the more you do with them, the more this decision makes sense. Okay. Hold on a second. I don't like, hold on. Let me see, there we go. Let me, okay, I'll lock it there. Okay. Okay. Now, so let's get some bigger matrices and see what the hell's going to happen. So what if I have these matrices? Let's not go too big. Doesn't matter, just numbers up. There we go, buddy. Keep going. You did it. So these I consider rows. These I consider columns. Now watch this. How big is this matrix? What's the dimensions?
2 by 2.
2 by 2. And of course, this is 2 by 2. So this is 2 by 2. And now watch. All right. Maybe I'll make this point next. But right now, why is this multiplication going to work? Because do you see how long this is? Isn't this 2 elements long? And it has to match up with this is 2 elements deep. Because I'm going to do this with them. All right. This will become clear when I see now that's a little too bright. I can't get this right. Hold on. Sorry. Can't really see that. There, all right, that's a little too dark. It's a little too bright. Hold on, everybody. There's got to be a happy medium somewhere. Screw it. All right, we'll go with that. All right. These, all right, I'll make this point again in a minute, but right now we can do this. I want you to realize how many vector combinations can I make? There's 2 vectors going this way here, and there's 2 vectors going this way here, correct? Yes? So I can do this to this, this to this, this to this, this to this. So how many dot products should I end up with? How many? 4. So here's the beautiful thing. How do you think I'm going to accumulate all those dot products? I'm going to accumulate it in vector form. Sorry, matrix form. So watch this. First row, first column, I'm going to put it in the first row, first column. That's where that answer is going to go. It's kind of nice. Whatever I'm working with, that's where the answer goes. So if I'm working with the first row, first column, I'm going to put that in the first row, first column. So what do I get here? -2, minus 9. Is that cool? -2 minus 9. You guys with me?
Yeah.
-11. So again, it's just dot product. I just have to look across and then I have to look down. So this goes with this. So now this is going to have to be first row, second column, first row, second column. What do I get?
8.
8 minus 3.
5.
Does anyone, again, there were a lot of decisions that went into why we do it this way, but it's a nice kind of way to organize results. So I'm kind of collecting all the possible dot products of the vectors here and the vectors there. I'm collecting them in an organized way. Now, believe it or not, when you do more stuff with matrices, it goes beyond just looking at them as these vectors. But this is the basis for how we define matrix multiplication. I don't know how you guys are doing, but again, it's really this simple. You take, I'm gonna do this and this. So I'm gonna look, -1 times -1 is 1, plus 15 is 16. That was the second row, first column, second row, first column. Second row, second column is going to be here. -4 plus 5 is 1. All right, maybe. And then you might realize that I can look at this as a vector, and this is a vector, and this is a vector, and this is a vector. It depends on what I want to do next. Let me see. Let me show you a little bit about what I meant about linear transformations. So watch. All right, I'm going to erase all this. You ready? Now watch this real quick. What if I do, what does this look like? It might be a special matrix, especially because I said something. All right, see if you guys, this might be a little bit of a weird one to make you do on your own, but it's not hard, it's just special. So let's see what we get if we do this. Let's do this together. So I'm going to do there and there. Yes. So it does take a little getting used to. You've never multiplied anything like this, but I have to do this times this. You with me? So I'm going to get -1 plus 0.
Yeah. So -1.
-1. And then I have to do this times this. So first row, second column is going to go here. 4 plus 0.
4.
0 plus 2.
2.
0 plus 9. So what does this matrix act like?
It acts like 1.
It acts like 1. We call this the identity matrix. So if I multiply something with this matrix, it leaves it the shit alone. Now watch, just stay with me, I'm not going to go too deep down this direction because this is something that we don't necessarily cover, this idea. Good Lord, I need to get somebody professional to come out here. But this is something we can do right now. Now watch. How is this different? What did I do here? All I did was I switched those, right?
Yeah.
So watch the effect it has on this. Let's see if it has any effect. 0, 1. So 0 plus 2 is 2.
Yeah, okay.
And then I'm going to do here. 0 plus 9 is 9. -1 plus 0 is -1. 4 plus 0 is 4. Didn't I just do that?
Yeah.
So this matrix transforms this matrix in a certain prescribed way based on how it's related to the what acts as 1. This is one step away from one. So when I multiply something by this, it does what happened to it. That's probably enough of that. Every matrix that I multiply something by is a set of commands. It's a set of, I don't want to say it. I don't know. It's like a little computer program, especially with all the zeros and the ones.
Or it could be looked at sort of like a filter too, right? Like you push something through it and it distorts how it comes out.
Yeah. Depending on where the zeros are, you can filter out certain things. That's another. Yeah. I think you meant it in more general sense, but
yeah.
Yes, I like it. It's a filter. It's a set of algorithms. It's a process to follow. Anyway,
It's a program.
it's a program. It really is. So I'm going to take all this away. So all you have to come away with is how to multiply two matrices. So let's make some bigger matrices and see if I can multiply them. Or some different ones. Can I multiply, you can do it, Jeff. Yeah. Can I multiply these together? What do you think you have to check? Can I multiply these together? What would I try to do? I would try to do this times this. And do they match up?
Not really.
Yeah, I can do 2 times 1, -3 times -3, and then void times 0. It's like, we can't handle the void. I don't know if you guys understand. It's not even 0. It's just that nothing exists there.
It's undefined.
Yeah, it's even worse than that.
It's worse than that.
Indeterminate. So what size is this? This is 2 by 2. Let me just say that. What size is this?
3 by 2.
3 by 2. In order for matrix multiplication to work, this and this have to be the same.
Okay.
Right? The number of columns has to equal the number of rows. Because otherwise you get somebody with no partner to go with, right? It's not even nothing. It's the absence of anything, including nothing. That is weird as shit. So I can't do that. What if I turn these around? Right? What if I put, I have no idea if you guys are still with, I know Austin is with me. I don't know if anybody else is out there. What if I turn these around? Can I suddenly do this somehow? This normally doesn't work with any numbers. If I turn them around, I get the same answer, don't I? 5 times 4 is 4 times 5. But is this doable now? Yeah. This is 3 by 2. This is 2 by 2. Those match.
Yeah.
And look, if I do this, doesn't it match perfectly with that?
Indeed.
Indeed. And how big is the answer going to? So here's what's cool. The inner things have to match. The outer things are how big the answer will be. 3 by 2. It tells me how big the answer will be.
Okay.
Oh,
That's
isn't
neat.
that nice? So now, if I do this, 2, I really want you guys with me because this isn't difficult. It's just different. 1 times 2 is 2. 2 times 4 is 8. 2 plus 8 is 10. 1 times -3 is -3. 2 times 1 is 2. -3 plus 2 is -1. So I'm looking there, 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 there. It is a very different way to multiply than we're used to. But again, there's a reason for the method they chose. They had decisions to make. They made the decision based on other things that come later. So I get -6 and 16 is 10. That's neat. And then I get 9 plus 4 is 13. Then I get 0 plus 20. And I get 0 plus 5. Jiminy Jeebus. Get in there. Okay.
Can you point one more time to show how you multiplied? I was writing and not looking at the same time.
So you go, this times this is going to be the first row, first column. 2 plus 8. Do you see that? 2 plus 8.
Yeah.
It's exactly the same as a dot product.
Okay, but you don't touch the 3 and the 5 into the bottom, or the 0 and the 5 into the bottom.
Yeah, exactly. So I'm doing the first row, first column, that's the answers there. First row, second column, -3 plus 2, then answers in the first row, second column.
Okay.
So if I do the second row, first column, then answer's got to go in the second row, first column. -6 plus 16, 10, and then so forth. All right, so now watch this. Let's see if we can get something freakadelic. Let's see. So what about if I had something like 2, -1, 3, 2, 1, -2, and then I have 4, 0, -1, -5, 2, 1. Can I do those? How big is this one?
3 by 2,
3 by 2. How big is this one?
2 by 3.
2 by 3. So am I able to do this multiplication?
Yes.
Yes, because these are the same. Check. How big will the answer be? 3 by 3. It's going to be 3 by 3. So go ahead and do that. I'll sit here and wait. Or stand, I guess. I'll stand. That's all right. I understand if you get kicked out. Few people having some issues. Okay. Oh, now I got. It's funny. It's back. Okay. Not sure what that means. All right. So it'll be 3 by 3. So we kind of catch up to you guys. 8 plus 5. 13. We good so far? 0 minus 2 is -2. -2 minus 1 is -3. How's everybody doing so far? Oh yeah, the song I know. I got the Oompa Loompa thing going on. So then we got, is that okay so far? You gotta let me know if this isn't making sense. It isn't hard, it's just different. So now I go this. 12 minus 10 is 2. This, 0 plus 4 is 4. This, -3 plus 2 is -1. 4 plus 10 is 14. 0 minus 4 is -4. -1 minus 2 is -3. Woo! Okay, all right. Not difficult, just different. Would this work if I turned it around? Probably, or else I wouldn't be taking the time to write it down. But why does it work? Well, because this is 2 by 3, and this is 3 by 2. Do the inner ones match? Yes, check. The size of my answer is going to be 2 by 2 now.
Interesting.
Interesting, yeah, because now this goes with this, So I'm going to have 4 things. That's why 2 by 2 is going to work. So I'm going to get 8 plus 0 minus 1, 7. Negative 4 plus 0 plus 2. I forgot already. It's negative 2, I think. All right. Negative 10 plus 6 is negative 4 plus 1 is negative 3. 5 plus 4 is 9 minus 2 is 7. Okay, I think that's right. I believe it's right. All right.
The answers are so different just because we changed the order.
Yes, this is the weird thing. This choice on how to do matrix multiplication means that matrix multiplication is not commutative. If this is matrix A and this is matrix B, A times B does not equal B times A.
Okay. All right.
Now, could there be some that it does equal? Yeah.
Yeah.
If I do matrix 1 times matrix 1, it's matrix 1 times matrix 1. And that's kind of cheating a little bit because then they're the same thing. All right. I like it. Flippity flu. Okay. Let me erase all this. You guys ready? Let's see. What time is it? Can I develop? Here. Can you do it, Jeff? Probably not. Wow. Hold on. Hold on to your butts. Yeah, okay. Sorry, hold on. Sorry. And then you can do it, Jeff. What's another thing I could do? I don't know. Sure. All right. I think that'll work. Yes. All right, let me show you something kind of weird. You ready? With normal numbers, what's the only way I can multiply 2 numbers and get 0? What's the only way I can multiply 2 numbers and get 0?
If one of them is 0.
Yes. What do you think the 0 matrix is? Isn't it this? Isn't that the 0 matrix? Yes, that's the 0
Yeah.
matrix. I like it. That's the 0 matrix. If I add this to something, won't it stay the same? Yes. Right. Add this to any other 2 by 2 matrix, it will stay the same. But watch this. What is? You can remember this, can you? Can you take a minute and do this? Are either one of these matrices a 0 matrix? Did I get that right? Is that the wrong way around? It's the wrong way around. Hold on. Are either one of these the 0 matrix? No. But what is this? 4 minus 4 is 0. Negative 4 plus 4 is 0. 2 minus 2 is 0. Negative 2 plus 2 is 0. Holy shit. Isn't that neat? Sorry.
It's kind of like, that's interesting. Yeah, it's really cool.
Okay. It's kind of like something I don't have an analogy for. I understand.
Yeah, exactly.
I understand. That's like a thing. That's like the thing that I would analyze something else with. I understand. That's just a little weird aside. And that's just because of the choice of how we develop this multiplication. Okay, now let me show you. I do have, thank God, a matrix multiplication handout. Right? Thank the gods. Let me show you what it looks like. Oh, where am I? Here I am. Okay. Oh, I'm tired, man. Let's see. I had 2 classes and 2 meetings today. That was awesome. And this is my 3rd class. Here we go. All right. Oh, I haven't. All right. Now it's active. So if you go to, I was going to say, if you go to Matrix, if you go to Canvas, you'll see this matrix multiplication handout. So it's got a nice example, a nice little example done. It's got another example. I'm checking the dimensions and then I'm multiplying. Okay, so that's a reference for you guys. If you're doing the homework, you got that sheet to reference, right? Is that all right? You guys okay? No, you hate it? Okay. Oh,
The handouts are always usually helpful.
Okay, that's what I try to do. Let me show you one more thing and then we'll call it a day. I kind of want to get us ready for the next thing we're going to do. Let me just throw something up here. Can you guys please take a minute? Come back here. Oh, Jesus. What do you want? Nothing, Jesus. All right, here we go. All right, don't worry about the equals part yet. Can you multiply this side out?
Aren't the dimensions wrong? Oh no, I guess they aren't.
No, yeah, this is 2 by 2.
Yeah, and it's
this
2
is
by
2 by 1.
one.
Yeah.
All
Yeah.
right.
Now there's variables there, but who gives a shit? They're not gonna be like terms, right? So big deal. So what am I gonna get?
X minus y.
2x minus y and
X plus 4.
now watch this. This is the first time you've seen matrices inside of equations. But what do you think has to be true if this is to be true? What's 2x minus y have to equal?
7.
7, right? And what's x plus 4y got to equal? 1. So I can represent a system of equations in matrix form, which is kind of like, okay, sorry, who gives a shit, Jeff? So there are things I can do with matrices that I cannot do with this directly. So we're going to learn a couple of ways to solve a system of equations quicker if I write them in matrix form, right? Would you ever want to solve this equation here by hand? You guys understand what I'm doing over here? Do you guys see this? Are you guys understanding what's happening? Do you want to do this by hand? Don't I need one more equation now? Yeah, do you understand? Wasn't it gross enough when it had 3 letters and 3 equations? Now I have 4 letters and 4 equations. This would take for freaking ever. I have to kill 1 letter 3 times, get a system of 3 equations, kill another letter 2 times, get a system of 2. Oh my God. And just imagine if I just put more and more letters and more equations. If I learned how to do it with a matrix, the amount of work barely changes, no matter how big this gets, no matter how much shit I throw in here. The amount of work does not change as much as it does if I add more and more equations to this. So the next thing we're going to do is figure out what methods can I use to solve a system of equations if I write it in matrix form instead. Is there anything to gain from this? Yes, there's a shitload to gain. So we're going to do that next. Otherwise, we're done, man. I'm tired. We're done for today. So the quiz should be unlocked right now. So if you wanted to go start on it now, you totally could. I've given you until Wednesday morning to get it done. So you got some time. Wednesday morning at 8 a.m. So you have until then to get it done. Oh yeah. Okay. That's it, guys. Let me know if you have any questions. Otherwise, get the hell out of here. And I'll see you guys tomorrow.
The matrices seem a lot more fun than I thought they would.
Yeah, it's really, yeah. The basic computations aren't hard. the amount of stuff you could do with them is quite a bit. Especially after tomorrow, I think you might appreciate them more. I don't know. We'll find out.
Yeah, or I'll hate them more. One of the
Yeah,
two.
it could go. You're right. It totally could. We'll see if I'm able to sway it one way or the other.
No worries. Have a great day, Professor.
Take care. Everybody else all right? All right.
Hey,
I'm gonna head
Professor.
out. Oh, yes.
Question, sorry. So
Sure.
could I ask again about question 68 on section 10.8?
All right. 10.8. Oh, come on. 10.868. Was that the one with the person walking all over the place?
That one was the one, the airplane.
Oh, the airplane. Okay. All right. What's up?
So you talked about how you want to break it up first. So like, and then you found the first vector, which was 0 and then 500. But how would you find, because I understand the process of how to get like the rest of everything, but I'm having trouble like finding the second vector, like that second part.
All right. So this is going, so it's from the northwest. So that's why I drew it going here. Is that
Yeah.
cool? Because it's from the northwest. This is a 45-degree angle. So you just have to break it up into its components here.
Okay.
Yeah. So then you've got, this is 0, 500, because that of course is completely on the y-axis, at least as far as I have my coordinates. And then this is going to have, I'm going to add to it the vector for the wind. And it's going to have a negative y piece and a positive x piece. You just have to figure out what those are, and it's like somebody said, it's cosine and sine of 45 degrees, right? So this
Okay.
it's 50. So this would be like 50 cosine 45, 50 sine of 45, and yeah.
And that's how you would find the other part of the vector, and then
And then
add-
if you add those together, whatever you get as a result, you do the inverse. What is it, one again? How many degrees off course? That's going to be the inverse tangent of the y piece over the x piece of the result. That's how you always get the angle a vector is at.
yes.
And
And-
this plane speed relative to the ground is just going to be the length of the resultant vector, right?
Okay. So that would be the magnitude technically?
Yes, the magnitude.
Awesome. All right, cool. That's just what I wanted to know, the 50 cosine 45.
Everything about vectors is easier if they're written in component form.
Mhm.
That's why on these kind of problems and with the person walking all over the place, you break everything down in component form, because then you can add them directly.
Awesome. All right, sounds good. Thank you, Professor.
You're welcome. All right, everybody else okay? Okay, I'm gonna head out. I'll see you guys